Students, we are sitting in ANSYS Antenna Innovation Lab of EC Department at the Karnataka Institute of Technology, Coimbatore. I am Dr. Ramasamy, Professor in ECE and Dean Academics and Research. Actually, this lab has been established with the grant received from AICTE, All India Council of Technical Education, New Delhi, under RPS, Research Promotion Scheme. And the purpose of establishment of this lab is to promote research among UG, PG students and PhD scholars, and also among the faculty members. And we have two major facilities in this lab. One is ANSYS HFSS software, high frequency structural simulator software. We got 5 user license plus 1 research license, and this is the hardware equipment, which is a 14 gigahertz vector network analyzer. So using this we have done many research work. Many UG, PG students, including pre-final year students, they have done many projects, final year projects and so on. Even the faculty members, we do research. I am the principal coordinator of this AICTE RPS scheme, and Dr. Sapna is the co-coordinator. Now the goal of this presentation can be regarded as one of the innovative teaching learning methodology used to improve your learning methodology in the field of design, simulation, fabrication and testing of microstrip patch antenna. Now, as I told you, we have done many research, and one of the research work that we carried out in this lab is novel wearable monopole antenna with controlled SAR for biomedical application, and it is using metamaterial technique. And the antenna that we developed, it looks like this. The uniqueness, the novelty of this work is that, as you notice here, the patch of the antenna. Actually, there are 3 elements in this antenna. One is copper plate, ground plate, and above the ground plane there is a substrate which is flexible substrate, which is known as PDMS, and above this substrate we have a patch, and the length of this patch is 1/4 of the wavelength. That's why it's known as monopole antenna. So there are 2 unique characteristics of this antenna. One is the patch, which is having 3 alphabets of KIT, mimicking the name of the institute, Karnataka Institute of Technology. That is one uniqueness. And second novelty here is the substrate, which is very flexible because it is meant for wearable applications. For example, it is meant for biomedical application. In the hospital, patient may fix this antenna on his body, and using many sensors will be able to capture or predict the vital patient body parameters such as body temperature, pressure, heartbeat and so on. And after sensing, it will be radiated by the patch to the doctor located at the remote places. Okay, so that is the application of this. So the antenna, it looks like this. The type of feed that we have is a coaxial connector, and the positive terminal of this connector will be connected to this radiating patch, and the negative terminal of this connector will be connected to the ground plane. Now, the traditional antennas available will be using rigid substrates, for example FR4, Roger, RT Durai and so on. So those substrates may not be suitable for wearable application, and hence we use PDMS. and the antenna designed is to operate in ISM band, in particular 2.45 gigahertz. And the specification of this dielectric, this substrate, it is PDMS with thickness of 1 mm, and the permittivity of this substrate is 2.7, and del, the last tangent of this substrate, is 0.014. And both the patch, the first characteristic to be evaluated is return loss versus frequency, and it has been designed for 2.4 gigahertz. So exactly at 2.4 gigahertz it's resonating, and the return loss is minus 40.63 dBi. I means isotropic, reference to isotropic antenna. So which means that most of the power excited through the coaxial port is being radiated in the single direction. Only less than 10% of the power is being reflected. So it exhibits good return loss characteristic. And the second important characteristics to be evaluated for this antenna is VSWR. That means voltage standing wave ratio, which defines the extent of mismatch between the source and the load. Okay. Ideal value of voltage standing wave ratio should be 1. But in practical, it may go up to 2. But in our case, it is 1.01 something. So it is a good match. So VSWR is also good. And the third thing is that we need to obtain the radiation pattern of this antenna. And this shows both E plane and H plane radiation pattern. And then we measure the gain of the antenna. At 2.45, it offers the maximum gain, and the maximum gain offered is 1.9067 dBi. So the gain is a little bit low, which needs to be improved. And another major characteristic to be evaluated is SAR, specific absorption rate. You would have noticed in your mobile phone, and it should be as per FCC standard, it should be less than 1.6 watts per kg for 1 gram of tissue. Okay, if you consider for 10 gram of tissue, it can go up to 2 watts per kg. Okay, but during simulation we set for 1 gram of tissue, so specific absorption rate should be less than 1.6 watts per kg. Okay, and using HFSS software, it has been simulated, but unfortunately the SAR value is 9.3437. That is the SAR, specific absorption rate. So which is beyond the FCC standard, which is not acceptable. So it has to be reduced below 1.6. So main thing is that the gain is 1.9 dBi, needs to be increased, and the SAR is more than 1.6 watts per kg for 1 gram of tissue, so which needs to be reduced. Okay, from 9.3 to below 1.6. So for this there are many techniques available, and the technique that we prefer is using metamaterial surface. Actually, metamaterial means there is no, in reality there is no such material. It should offer negative epsilon permittivity and negative mu permeability, and hence the refractive index will also be negative. So in reality there is no such material. So we artificially make, and we simulate unit cell metamaterial. Okay, actually it looks like this. The same PDMS substrate. On either side of this substrate, PDMS substrate, we have copper strip, which is nothing but a square split ring resonator on both ends, top as well as bottom. This is also designed for the same frequency of 2.45 gigahertz. Now, the concept is that it's going to act as a reflector.
reflect. I told you that when you feed 100 milliwatts excitation, more than 90% of the RF power will be radiated in the forward direction, and only less than 10% will be reflecting back. Okay, we want to make even this 10% to be, spread in the forward direction. So for that purpose, we are using this as a reflector. That's why both are being designed at the same frequency of 2.45 gigahertz. Okay, so now the purpose of using this is to increase the gain and reduce the specific absorption rate. Now, after building this, it has been the performance of this unit cell has been simulated using HFSS, and the magnitude as well as phase of S11 characteristic has been obtained. From that, the real and imaginary part of epsilon and mu has been obtained, and we confirmed that both epsilon and mu were negative, and hence the refractive index is also negative. So it exhibits its double negative material characteristics. So we have decided to use this meta material to improve the gain as well as reduce the SAR. Now your real antenna will be having two layers. Okay, one is the bottom one, meta material, and we have simulated three kinds of arrays, 2x1, 2x2 and 2x3. Okay, and since it is variable application, we need to go for miniaturization, and that's why we have selected this one, 2x2 metamaterial array. Now, so your antenna system will be having two layers. One is this is the bottom layer, above which we will be placing this. Okay, with a gap between these two, and this gap between this antenna and the metamaterial surface has been optimized. Okay, and daily for about 17 millimeter optimization has been achieved for better performance. Okay, so now with this metamaterial we simulated the performance of the antenna system. We obtained the SAR. Now SAR, earlier it was 9.3, now it has been dramatically reduced to 1.1074 watts per kg per 1 gram of cell, and the gain has also been improved. Okay, so the gain after using metamaterial, it has been improved to 4.61 dBi. So earlier it was 1.9. So there is a considerable improvement in gain as well as reduction in SAR. Okay. Now, so simulation is over. We thought of, since we satisfied with the simulated performance of this antenna, we thought of going for fabrication, building miniaturized antenna. So this is the antenna that we have built. So after simulation, the Gerber file has been transferred to CNC, and we use wire mesh cutting technology to cut both the radiator as well as the ground plane, and using glue it has been fixed above the PDMS substrate, and below this substrate we fix the ground plane, and the type of connector we use is coaxial cable. Okay, the positive terminal of the connector was connected to the radiating patch, and the negative terminal was connected to the ground plane, and we feed some excitation of 100 milliwatts, and we measured the voltage standing wave ratio as well as gain of the antenna fabricated, and it was 4.38. Simulated was 4.61, and there is a little bit reduction in measured gain by 0.3 dBi. Okay, and VSWR also almost near to 1.1. Okay, so this is the concept that we use to enhance the gain as well as reduce SAR, and as I told you, the application is for biometric biomedical application can be used by the patient in the hospital to radiate his body parameters to the doctor located remotely. Okay, so the conclusion is that this is the vector network analyzer. This is for the measurement of return loss. The simulated return loss, it was around minus 40 dB at 2.45 gigahertz. So the antenna has been fixed to one of these two ports, and we at around 2 gigahertz, 1.94 gigahertz. There is a little bit difference between the simulated one and the measured one, but both are comparable. Okay, so this is the work that we have done. So I conclude that this antenna is best suited for biomedical application, and which is resonating at 2.45 gigahertz ISM band, and gain without metamaterial it was 1.9 dBi, and the SAR is 7.33. So both have been gain has been increased and SAR has been reduced below 1.6, and it is readily available. Okay, so as I told you, the purpose of this innovative teaching learning methodology is to encourage you people to take up similar mini major projects in your curriculum. Okay, and I hope this will have been useful for you. Thank you so much.
இப்போ டெய்லி ரூட்டீன் டெய்லியும் டாக்டர்ஸ் வந்து பேஷண்ட்டை வந்து பார்க்கறதுக்கு பதிலாக டாக்டர் இருந்த இடத்துல இருந்து பேஷண்டோட நிலைமை என்ன அப்படின்றது பேஷண்ட்டுக்கே அனுப்புற மாதிரி.
Exactly. For example, during COVID season, right? Doctors may not be available and may hesitate to attend all the patients. Okay. In that case, the patient will be isolated, and the doctors may be available in a remote location. Okay. If you could fix this wearable antenna, the wrist arm of the COVID affected patient, which will be sensing, but we might be using many sensors. Okay, for temperature prediction, one sensor, blood pressure sensing, another sensor, ECG, heartbeat to detect heartbeat, another sensor. Okay, so all these sensors will be sensing the vital body parameters, and that will be fed to this antenna, and those parameters will be radiated using this copper foil to the remote location where your doctor will be available. So doctor will be simply logging in and checking the patient parameters of X or Y and confirm whether everything is within the limit or not. If it is not within the limit, then arrangements may be made to take care of the patient. Otherwise, he will be left undisturbed. This is meant for that, exactly that purpose. Okay.
The cost,
see, the traditional way of sensing the body parameters and evaluating maybe time consuming. You need to visit physically the hospital, and you have to get appointment from the doctor. Okay, so you need to spend a lot of time. Again, elders, your grandfather, grandmother, they may not be able to even walk. They simply hesitate visiting hospitals frequently. Whenever you ask, they say, I'm all right, but they might be having some problems. So in that case, if you fix this antenna their body, they will be able to radiate the parameters. Cost-wise, very cheap. Okay, and this material we need the copper strip. Okay, we placed order on Amazon. It costs around 300-400 rupees. That's all. And this PDMS substrate, we prepared this PDMS substrate with the help of the nearby institute. Okay, which took around 5,000. Okay, and then testing. Earlier we went outside for testing, but now we purchased this vector network analyzer. Only for measuring the gain and radiation pattern, we need an anechoic chamber, which is currently not available in our premises. So we need to and then go out to test the radiation pattern. So cost wise it is cheaper. And this is the setup, anechoic chamber setup. Okay, the antenna has been fixed here. Okay, and the radiation pattern has been obtained, both E plane and H plane radiation pattern, and from that 3D radiation pattern we evaluated the gain of the antenna without metamaterial, and then since the gain was low, we use this concept metamaterial to increase the gain. So this is the vector network analyzer, and this is the anechoic chamber facility. Okay, these are the snapshots of our antenna. Without this is without metamaterial. This is with metamaterial fabricated antenna. Okay. Thank you so much.
Thank you.